Guys, today we are back with another problem, and today's problem is solving the n queens puzzle problem. So this is the n queens puzzle problem and placing n queens on the n cross n chessboard such that no two queens can attack each other. Given an integer n, find all distinct solutions to the n queens puzzle. Each solution contains distinct board configurations, the n queens, the placements where the solutions are permutation of in the increasing order. Here the number in the ith position denotes the ith column queen is placed. Okay. So before solving this particular problem statement, make sure you guys go and check out my DP series, and make sure you guys go and check out my recursion playlist as well. So today's problem is on n queens problem. Today's problem statement is on n queens problem. So guys, be very careful while I am solving this. This problem is going to be solved using the process of recursion plus backtracking. So how we are going to solve this problem? So before solving this, always remember you don't have to always know that you have to solve anything with the help of knowing the game actually. So you can solve this problem without even knowing how to play the chess. So here are some constraints in which I will describe how and what is the n queen problem all about. So let us take a 4x4. Let us take a 4x4 chessboard. So there will be 4 rows. So I can say n cross n chessboard. So I can say n cross n chessboard. Okay. So if you see carefully, there is 4 rows and 4 columns. 4 rows and 4 columns. I can give the indexing as 0, 1, 2 and 3. Similarly over here 0, 1, 2 and 3. Okay. Once I am given the indexing 0, 1, 2 and 3, I am going to position the queens in the chessboard. I am going to place the queens in the chessboard. So say for example, I'm putting a queen over here, I'm putting a queen over here, and putting a queen over here. So now the condition is, you will ask me, Arnav, why did you place the queens like that? What is the logic of this n cross n chessboard and why we are using this? So there are some constraints. Okay. So the conditions I will write like this. Every row should have a queen. Okay. This is first condition. Second condition is every column should have a queen. So this is my second condition. Now the third and the most important condition is none of the queen should have attacked each other. Now you will say me, what does this actually mean? So let us, before coming to the third problem statement or the third constraint, let us first try to check whether my first two constraints are valid or not. So my first condition is every row should have a queen. So let me check. Row number 1. So if I say this is as row and this is as column. So first row has a queen? Yes. Second row has a queen? Yes. Third row has a queen? Yes. So all the 4 rows have a queen. Now let us come to the columns. The first column has a queen, yes. Second column has a queen, third column has a queen, fourth column has a queen. So the first two conditions are fulfilled. But none of the queens should have attacked each other. So you are saying that the queens are diagonally placed in this example. But can you prove they are attacking each other? Yes, they are definitely attacking each other. So before knowing how the queens are attacking each other, you should know the rule of the chess, which says that in order to make a queen attack each other, a queen can attack in the following directions. How many directions? 8 directions. There are total of 8 directions a queen can attack. So I'm going to mention the 8 directions. The queen can attack top, bottom, right, left, this diagonal, this diagonal, this diagonal, this diagonal. So 3, 4, 5, 6, 7, 8. So you can see there are total of 8 directions the queen can attack. So what is this direction? This is this direction. This is this direction. This is this direction. This is this direction. To my bottom right diagonal, which is this direction, the queen is attacking. Therefore, this particular arrangement of the queen is not possible. I cannot return the answer of this particular arrangement. So let us try another example and try to analyze with the fourth example. So first, my condition is to draw the checkerboard. So I have drawn the checkerboard like this. I've drawn the board like this. Okay. Once I've drawn the board, I'm going to draw the columns. Now I'm going to place the queens in such a manner that all three conditions are satisfied. So let me place the queen over here. Let me place the queen over here, and let me place the queen over here, and also let me place the queen over here. So in this condition, first is every row should have a queen. Yes, every row is having a queen. Every column should have a queen. All the columns are having a queen. So this condition, both the conditions of the first two are fulfilled. Now the question is, no queens can attack each other. Now let us come to this particular queen. Is it attacking any queen? See, if it is going down, there is nothing. If it is going here, nothing in the diagonal as well. So it is safe. So it is safe. Let us. So it is safe. So over here also this is safe. This one is also safe, and this one is also safe. So you can see there are four queens which are safe. Four queens which are safe. All the four queens which are safe. You can clearly see that. So this condition is also fulfilled. Now let us try and understand with one last example and check whether this is valid or not. So if we particularly take another example, another 4 cross 4 matrix, if I'm taking another 4 cross 4 matrix, so this, and this. So what will be the position? Say for example, I'm placing a queen over here, a queen over here, a queen over here, a queen over here. So condition 1, all the rows are present. Yes, all the rows are present. All the columns contain at least one queen is satisfied. Okay, so you can see in this n cross n or 4 cross 4, it is satisfying all possible conditions. So this is one possible condition which is fulfilled, and I can say this is as well as safe. I have to return the coordinates and the position of the possible values. Okay, so how I am going to solve this? I am going to solve this using recursion. Solve using recursion. So how recursion and backtracking actually works? So say for example, draw very small and very easily so that you can understand. Say for example, I'll be having an empty square like this. I'll be having an empty square like this. Okay, and what I can see is the first try will be to definitely put a Q over here. Yes. Now when I'm subdividing this problem, when I'm subdividing my problem, I am having another queen, another matrix like this. Okay, this is how recursion actually works. So if you carefully see, I put a queen over here. In the first row, the queen is already occupied. So where should be my queen in the second row? Can the queen be placed over here? No, the queen cannot be placed over here. Why the queen cannot be placed over here? Because if I place over here, then it is attacking. So I cannot put anything which is I plus 1 in this direction and which is column in the same direction and I plus 1 in this direction. Okay. So what I will write, I cannot put over here. What about this position? Can I put a queen over here? Yes, I can put a queen definitely over here. So in the first two row, I put the queen like that. Now let us come with third example. Okay, in the third example, no, I cannot put another queen. So I have to move to another, I have to move first column, row, then column. So now let us fill the column. Okay, so let us come to this direction. So can I put a queen over here? No, it will attack. Can I put a queen over here? No, it will attack. Can I put a queen over here? Yes, you can put a queen. Now come to the row. This row is done. Now coming to this row. When I'm coming to this row, I can see, can I put a queen over here? Can I put a queen? No. No, I cannot put a queen over here. Can I put a queen over here? No. Can I put? No. Can I put a queen? Yes. So I have completed one row, two row, one column. Now next column. Now coming over here. I have to check. Can I put a queen over here? No, I can't. Can I put a queen over here? No. Here, no. Here also, no. So I can't put queen over here as well. Okay. So again, then I have to remove this and backtrack this to my original channel and make it another matrix, similarly which will divide into another matrix, and all the possible combination has to be dealt. This is done using the help of backtracking, okay, plus recursion. Okay, so let us go with the code and explain you the code in strategy. So here is the code. First we will be given this particular function, array list. The function will return an array list of type integer n queen n. So this is the method to find all possible solution for n queens. We are taking a solution in the array list. Our list will store all the solution to store all valid board configurations. After that, we are making a blank board to store the current board configuration. Then we will be start solving from the first row. So we'll be calling the solve function, and we are passing the first row as 0, the total number of rows and column as n, the board where we are going to implement our solution as board, and the solution is the list of the solutions. Finally, we are going to return the solutions. So where is my solve function? So here is my solve function. I'm taking a row, I'm taking the length, I'm taking a board array list, I'm taking a solution array list at the same time. Now let us come to the int row. So int row equals to n, it is saying that if my row, if this is my base condition, so I can say base condition, this is my base condition, then what I'm doing is solutions dot add new array list of board. So I'm basically adding the solutions to that particular board and returning it. Okay, now we are trying to place a queen in each column of the current row. So I'm starting the column as 1. Okay, I'm starting the column as 1. So this is 1 base indexing. So I'm starting the, no, sorry, this is 0 base indexing. I'm starting the column as 1 for the first column. Okay, and I'm traversing it from column is less than equals to n and column plus plus. So I'm checking whether it is safe to place a queen or not. So I made a save function check. So in the save function, I've taken the board and row and column. So I'm iterating through all previously placed queens to check for config. So I can say placed column equals to board dot get I. So it helps us to check whether there was any previously queens over there or not. Lastly, we are checking if the queen in the current row is the same in the same column or in the same diagonal. As I told you, I cannot have a queen over here, here or here. In all the 8 directions, I have to be very careful that it cannot be placed. That is the condition. If the placed is in the same column, or the mat dot absolute value of the placed column minus the column is equals to mat dot absolute value of I minus row. So this condition helps us check whether it is in the diagonal or not. Okay. After that, we were returning false or we are returning true. Now let us come back. So whenever we have checked, oh, this is safe to put, we can call the board dot add to add the columns. Lastly, we are again recursively calling this function solve. And in the solve function, we are recursively calling it from inside. That's why we are backtracking. Why we are doing row plus 1? Whenever we are doing row plus 1, we are iterating to our next row, which I already explained you over here somewhere, that we can go to our next row. Okay. Similarly, we are putting the n and everything. Lastly, we are going to remove the board dot size of -1. Okay. Why we are removing the board dot size -1? We have to remove the queen from the current row and try the next column. So current row is already filled. The queen is already filled. Now my task is to place the queen into some other column or not. So for that, I'm going to remove the queen from the current row and initially put it to the next column. And this process continues recursively. So this was about the backtracking concept of the particular problem statement. So first task is to make a solve function. In the solve function, the valid is safe function should be made to check whether the queen is safe or not. Queen is only safe, it is not attacked by 8 directions, it is present in every row and it is present in every column. So all the conditions are satisfied, then only we can proceed with this particular problem statement. Now let us try to understand why did we do that particular placed dot column is equals to column over here, or mat.abs value, okay. So if I carefully check, what I'm basically doing is I'm retrieving the column index over here. I'm retrieving the column index over the placed of the queen placed in the ith row. We are checking whether the current row shares the same column as a previously placed queen. And finally, we are also checking over here if either condition, if the queen in the current row is on the same diagonal as the previously placed. So this is the previously placed queen and this is the diagonal element, whether it is containing a queen or not. In either of the cases, if it is already present, that means there is a conflict. In case of a conflict, we are going to return a false, or else we are going to return a true. Okay, so in the topic tags, we can see the topic tags, it says backtracking, recursion, and algorithms. So make sure you guys like, share, and subscribe to the channel, and help me reach more subscribers. And we are looking forward to solve more problems in the future. So just quickly submit this solution. We are going to submit. And we have successfully completed 198 days. 2 more days to reach to our 200-day mark. Thank you so much and see you in our next video.